Hi,
Okay.
everybody. Welcome to our first round of Fellows Talks for Fall 2025. Um, we have a few interesting presentations for you today. First up is Hannah. Whenever you're ready, Hannah, you can get started.
Okay. Um, One moment. Okay. So my name is Hannah Havel, and I am a IRIS-HEP fellow, and I'm a senior studying computer science and mathematics at Northern Illinois University. And my project is with HS3 Support for Combine, which is enabling JSON-based workflows for CMS analyses. My mentors were Dr. Gali and Dr. Smith. So as an introduction, Combine is a framework widely used in the CMS collaboration to perform complex statistical analyses in a standardized and reproducible way. And it essentially allows physicists to perform combinations of measurements, share statistical models, and publish results. And the software is built on Root, RuFit, and RuStats, which handle modeling of event distributions, likelihoods, and fits. And Combine's core is based on is implemented in C++. So currently, Combine relies on root files to store statistical models and workspaces. And models themselves are defined using data cards, which are human readable files describing the likelihood model, processes, and uncertainties. So when running an analysis, Combine reads both the data card and the root file to create a RootFit workspace, which is then used for fits. So here I have the workflow and an example command. So here's an example of a data card, and as you can see in the red, it references a root file, which is essential, necessary for the workflow. So there are some limits with the current workflow. So right now, the use of binary root files makes it difficult to share or inspect models outside of root. And essentially, you cannot easily manipulate or view these files with standard data science tools. And then because analysis is tightly coupled to root, this limits interoperability with external frameworks. And possibly for non-CMS collaborators, it is going to be difficult. There's a lack of flexibility for future analyses with those outside of CMS. So the goal is to enable JSON-based workflows, and HS3 stands for High Energy Physics Statistics Serialization Standard, which is a human and machine readable JSON-based format. And adopting HS3 will modernize the workflow and reduce reliance on legacy components within Combine. So it's JSON-based, which means it is both human readable and compatible with modern data tools. And HS3 enables easier sharing and publishing of models and integrates naturally with Python, which is important. So in short, it makes high-energy physics statistical models more accessible. And here's an example of what an HS3 JSON-like model representation would look like. So the JSON file, and this is from the documentation of HS3. So in order to convert root to HS3 JSON, I created a Python script, and it can handle PDFs, histograms, processes and yields, observables, and metadata, etc. And custom export rules are applied using a file called exportkeys.json, which handles combined classes not natively supported by HS3. So the result is a human and machine readable JSON file, which can be pretty printed for clarity. So it just means it will have a better a structure where you can see everything clearly. And this step is the bridge between root-based combined workspaces and the JSON-based HS3 format. So here's an example of, here are some examples of my output files for using this script. So on the far left, I have an HS3 JSON representation of unbinned data. And then in the middle, the representation of binned histogram data. And that is directly from the root file that is associated with the histogram on the far right. So binned data is generally associated with those histograms. So as far as changes to support HS3 and combine, we added an HS3 flag to text to workspace .py, which builds rootfit workspaces from a data card. When this flag is used, the workspace can handle JSON-based components directly. For shapetools.py, this loads and processes shapes from root files for inclusion in the workspace. It was modified to bypass data frame wrapper.py, and this essentially tries to build pandas multi-index from the HS3 JSON reference in the data card under the hood, which was a problem, so we wanted to bypass that. And some of the changes I made to the shapetools file are to properly handle a JSON file reference, as well as specialized handling for unbinned root data sets using root keys PDF. And the biggest change is that it can load HS3 JSON files via a tool, so shapes can come from JSON instead of root files now. For modeltools.py, this now verifies root has root JSON factory WS tool, the tool that's crucial to this, and it imports JSON into a temporary workspace and ensures PDFs, observables, etc. are correctly loaded for fits. Most importantly, the original combined workflow is still fully functional if the HS3 flag is not used in execution. So to summarize, this is the new workflow with, and it's a two-step process. So I have the commands that would be used at the bottom. So with these updates, parts of the likelihood model can be converted directly to HS3 JSON. So now you can create a workspace in root using JSON input and allowing hybrid workflows when where some components are in JSON and the others remain in root. So fits are still performed on a rootfit workspace and preserves the established combined fitting framework. And so the summary is in that schema right there. So we have a data card that now is a reference to an HS3 JSON file, root files, optional JSON, and then this produces the workspace with both root and HS3 components. And then this is an example of a data card that references both a root and JSON file. For future directions, it's intended to implement importers and exporters for additional combined classes to increase coverage and to improve handling of complex systematics and nuisance parameters in JSON workflows, and then ultimately integrate HS3 fully into CMS workflows for large-scale analyses. So right now I'm working on documenting this HS3 approach to support its adoption and reproducibility for the next person that takes this on. So overall, this work lays the foundation for a more modern, interoperable combined workflow without breaking any of the existing functionality. And that's it.
Thank you, Hannah. Nice talk.
Thank you.
Do we have any questions for Hannah? All right, no questions. Thanks again, Hannah. Up next is Oleksii. You're up next.
Yes, one moment.
Okay.
Okay, so my name is Oleksii Hrechykha. I'm a master's student at Kyiv Academic University, and this summer my fellowship consisted of the work on the project that aimed to complete an array API compliant ragged library, and my mentor has been Jana Osborne from Princeton University. A brief outlook of the presentation is that we will discuss what are jagged or ragged arrays and how are they usually handled, what's array API, what are the differences between Ragged and other libraries which handle arrays, what are the things currently missing from Ragged, and at the end talk about what have my work been this summer. And to start, we will talk about jagged arrays. These are essentially arrays of lists of varying lengths, which arise in when you have a result in high energy physics where for a certain event, a particle would not have all of the possible parameters, for example. So it could have missing values, it could have empty elements, etc. And currently, the library that is most frequently used to handle such arrays is called Awkward, which allows for arrays or structures which are completely arbitrary and also consist of not just any types, but mixed type inside of one array as well. So you could have dictionaries, lists, tuples, ints, and strings, which is fine, but the problem is that if you were to standardize the arrays or the libraries which work on with arrays, Awkward could not by definition fit there because it's just too general. And why do we standardize, and what do we standardize for? Well, the community for which deals with or creates libraries for work with arrays have created something that is called Array API, which is a standard between an agreed upon standard between these libraries, which allows the user to have certain expectations regarding the functions an Array API compliant library would have, their performance, their behavior in general, and so on, while also allowing for some variation between the libraries. And Awkward does not comply with this. It could not possibly comply. And because of that, it's important to introduce a library which would. It's called Ragged, and it's currently being worked on, and it allows the user to manipulate Ragged arrays, but in an Array API compliant manner. An example of a Ragged array you could see right here, and one of the instances where you can know that it follows the Array API specification is that a shape of a Ragged array would have none values, which corresponds to the fact that you cannot name a length of a row which would be uniform along these dimensions. And so basically, Ragged is designed to work with jagged arrays. It complies to the standard we've mentioned before, and it's also fast, like Awkward or NumPy. And when compared to Python objects, Ragged arrays take up way less disk space. And when it comes to my work on the project, on this particularly unpretty slide, you could see a list of all of the various to-dos from GitHub repository, and to complete as many of them as possible has been my task. However, when compared to last year's work, which I did on the same project, me and Jana have decided to work on broad coverage rather than deep coverage, meaning that I have aimed to provide the first approximation or the first implementation of as many functions as possible, so that later on other contributors would finish up, for example, improve performance and so on. And throughout this year's project, I have managed to complete the to-dos which are highlighted in bold, and unfortunately I wasn't able to do some of the more interesting functions, or you could say that some functions are left for my mentor Jana or other contributors to finish. It is not by design, and the reason, for example, tensor or vector products weren't done is because it was decided to start from simpler functions, but then when you do a number of functions of a certain family, then you can see that there are differences, or rather the similarities between them, and it was easier to just keep working on a branch, and because of that some interesting things were left out, but the progress has been made, and the tests have been written, so it was a success. Oh, 1 moment. I think there's a problem with the slide. Excuse me. I'll just open it this way, because I'm essentially summing up, and I'd like to thank Jana Osborne, who has been very helpful to me throughout this summer and the previous summer, to IRIS-HEP for providing a framework for Ukrainian students to participate in international collaboration, and to Defense Forces of Ukraine, which make the aforementioned collaboration of Ukrainian students even possible. And the project has been funded by such bodies, and yeah, I'd be happy to take any questions if there are any. Thank you.
Thank you, Oleksii. We share the same sentiments, so glad you were able to participate. Any questions for Oleksii? Gordon.
Hey, can you hear me, first of all?
Yes.
Yes.
I'm in a very noisy environment. Okay, now that was a fantastic talk, and looks like a huge amount of work, so thank you very much. One of the
Thank
things
you.
I was trying to sort out with Ragged was, how it compares with the other library that we use a lot, like Awkward, and how much code gets shared between these two efforts. So, many of the algorithms that you have to pull out for Ragged, for example, probably already exist in Awkward. And is that something where you can just sort of cheat and rip? So cheat is in quotes, of course, since this is all open source. But sort of rip things out from there to make this
Yes, essentially, yes. I must have mentioned that Ragged is a wrapper around Awkward, so there are many things Awkward does which Ragged also should, and wherever possible we use Awkward while limiting its functionality. So Ragged, for example, could not have array elements which are not numbers, let alone allow for mixed types inside of one array that Awkward does. So
Right. I
yeah,
heard
so
you
yes,
mention
so
that. I
whenever
did not
possible.
appreciate the significance.
I'm sorry, could you repeat? I have talked over you.
I was just saying I heard you mention that, but I didn't appreciate the significance of that statement. All right. Okay.
Yes,
Thank you.
yes, thank you. We use Awkward or NumPy in some cases whenever is possible.
Yeah, makes sense. All right. Excellent talk. Thank you.
Thank you, sir.
Any other questions? All right. Thanks again. Up next is Rūta.
Thank you.
Hello, can you hear me?
Yes. Go ahead and share your screen.
Yeah. Hello, everyone. I'm Rūta Lomsargytė. I am a student in Vilnius University, physics bachelor's, and I was a IRIS-HEP fellow this summer. And my project was development of a large language model-based Copilot tool for CMS analysts. And my mentors were Peter Elmer, David Lange, and Gordon Watts. First off, about the project background, as we all know, CMS data analysis often involves complex specific tools, and existing documentation is fragmented, often scattered across a few sources. So we wanted to explore the possibility of integrating large language models into workflows. So there was this question, what if analysts could ask a large language model, could ask a natural language question about a certain data set and get working code? For example, if we wanted to plot the missing transfer synergy of all events in this certain data set, we could ask this question, let the Copilot handle the coding part, and get a histogram. To implement this tool, we set a few goals. The first one was to build a retrieval augmented generation pipeline. It's faster and uses less resources than fine-tuning, and also easier to update with new documents. So in essence, we have specific relevant documents and the user query. We embed them both and store them in a vector database. And then using the query, we recall the top matching chunks, pass it all to the LLM, and get an answer. Also, another goal was to write CMS-specific code hints, which is in its own ways like simplified documentation, and to test the quality of the tool. We used IRIS-HEP functionality benchmarks. So the retrieval augmented pipeline looks like this. It ingests the documents. In our case, it's markdown files using this unstructured markdown loader, and splits them into chunks by section, which every section is kind of guide on its own. And then for the embedding and storage parts, it embeds each chunk and stores them in the collection. Then the user input is also embedded and used to retrieve the top matching chunks. Then we move on to the generation and execution. The retrieved chunks are added to the prompt and then passed to the large language model, which was Llama 3 in our case. And the extracted code from the answer is executed and retried if we run into an error. And this is the setup that I used to run all of this. The so-called hint files were actually just simplified documentation for CMS-specific code, variable, and common error hints. And they all helped generate better code, since we know LLMs tend to hallucinate. So adding more detailed comments actually left less space for hallucination. And also the common error hint to help with the repeated generation, and sometimes the LLM doesn't know the exact variable names, so the variable name hint file also helped. Another thing that we saw improve the generation is a retry loop, where generated code is executed, and if an error occurs, the original question and the prior code, the error message are returned for another retry. So we can see in this example, there were 4 tries and the 4th one was successful. For some reason, it didn't know how to take the absolute value of a number, and a few retries helped it generate correct code. So for the testing, as mentioned before, we used IRIS-HEP functionality benchmarks. Another thing worth mentioning is that large language model outputs are non-deterministic, meaning the same question may yield different answers across separate runs. So it can generate code on some attempt and just incorrect on another. I would recommend checking out an alternative approach for Atlas with node chunking and tested across different models developed by Gordon Watts. And here's what the testing looked like. So we can see the top retrieved chunks for this second question, plot the transverse momentum of all jets of all events in this data set. So we can see that it recalls the first chunk was related to plotting, the second one important libraries, which we can see they are relevant, and then we pass both the query and the chunks, and the LLM generates code. And the results we got was that it could solve 4 out of 8 of those benchmark questions, the most simple one being the first one, plot the missing transverse energy of all events in this data set. It did fine. The most difficult one being the 4th question, plot the missing transverse energy of events that have at least 2 jets with PT greater than 40 giga-electron-volts of this data set, and it also did okay. And then where problems began was question 5, obviously. It was plot the missing transverse energy of events that have an opposite charge muon pair with an invariant mass between 60 and 120 giga-electron-volts. So it struggled with invariant mass calculation, and it plotted the wrong parameter as well. We can move on to the conclusions. the number of errors in generated code can be reduced with detailed hint files. However, in some cases, the issues still persist. Like, for example, it sometimes doesn't import a needed library, hallucinates random functions that don't exist, and also really struggles with arrays sometimes. Which leads us to our second point, that detailed documentation is the crucial part to making a large language model-based assistant. Moreover, running such tool with limited computing resources takes a significant amount of time, which was around 30 minutes for 8 questions, even without fine-tuning. Also, as we can see, it's effective for simple questions. However, large language models might be needed for more complex ones. And one thing I noticed was that chunk retrieval is helpful when coding manually, meaning that even if the large language model doesn't get the question correct, the retrieved chunks can still be useful if you choose to code by hand. The possible next steps could be expanding the documentation, the so-called hint files, and testing on models with a larger context window. And also, okay, that's it. This was the prompt I used and the project repository. Any questions? And also, I would like to thank my mentors for the help.
Questions. Gordon, go ahead.
Hey, Rūta, I just wanted to say it was a joy working with you. And if you ever decide to continue working on this, I'd be more than happy to continue to collaborate. Looking at your last set of, you had possible next steps. If you had, if you were in a place where you could just continue this project, what do you think would be the next thing that you'd want to work on, the next most promising thing to tackle to continue to improve?
Well, I would like to see how this setup works with larger models with larger context window. And that's, I think, we could move on from there if we saw the results. Yeah.
Okay. Mohammed?
Hi, thank you for the nice talk. This is pretty cool. Maybe it's out of my own ignorance, but I am unsure how this could compare to some commercial LLMs, like using ChatGPT for the same task or something similar. What's the distinction between the two things?
Well, the reason for creating this was that usually the commercial models don't know specific information for like specific experiments like CMS.
Do you have an because the examples you've shown here were using the open source, like the IRIS-HEP toolkits. So do you have certain examples of things that are more specific to CMS that you maybe trained it on or tested it again?
Sorry, could you clarify what you meant?
So
Mo, this is Peter. So one of the things to remember is that one could also move in the direction of proprietary things within one of the experiments that aren't part of the public training for with the ChatGPT that I've seen, for example.
Okay.
functionally.
Okay.
And that's sort of the interest in using it's basically a model with open source, the reg database. Is that we don't have to expose necessarily our stuff to ABIS, or to ABIS to CMS, or to the reg.
Okay. Yeah, that's
For
makes sense.
example.
Another thing that I find, sorry, go ahead. I was just going to say the other thing that I find very fascinating about all of this work that Root has done is that what comes out of the LLM depends a lot on what you put in the hint files. So there's nothing that stops you from generating a set of hint files for something that's completely internal and specific to a framework. This is this proof of principle that she's done is I think quite general. I did some work with some internal Atlas stuff, and it works if you give it the hints that it needs. It's much more flexible than I think. Certainly before she started this work, it looks much more flexible to me than I was expecting.
Right. Thank you. This clarifies.
Okay. Any other questions? All right. Thank you, Rūta.
Thank you.
Next up is Roman.
Yeah, my name. Can you hear me?
Yeah, we can hear you. You can say it.
Yeah, my name is Roman. My mentors are Mohammed Ali, Alexander Helt, and Matthew Faker, and I worked on Pythonic histogram smoothing tools. So why we choose such I think histograms are extensively used in high energetic physics, especially large hadronic collider for analyzing it, but results can be noisy, and to extract some better results from histograms, we use smoothing, but we have a problem that there is very little instruments and tools for it. Instruments that exist are very not user-friendly, hard to install, and poorly documented. And there is no instruments integrated in scikit-HEP ecosystem. So we want to create libraries that would be integrated into scikit-HEP ecosystem, would be documented and easy to use. So about what already done is moving running median. It's simple smoothing. Here, as you can see how it works. We specify some windows. For example, you can see here is red boxes is the windows of 3 values. From these 3 values, we choose median and keep it in smoothing version of the data. And we do it for each for each value until we left with endpoints. In endpoints, we can just keep them or use functions to calculate them. Next is Hanning or moving radian median. It works pretty much the same as previous one, but we only choose from windows of 3. Previous one we can specify, for example, 5 or 7. Here is only 3, and we calculate sum of the quarter of left and right plus half of center value. And we keep endpoint values and don't use any function to calculate them. There is additional version of this like function, conditional. We apply it only if signs differentiate, signs of the values differentiate, as you can see on the right side. And if they don't differentiate, we just keep them as it is. When we smoothing, with previous functions, we can create natural peaks of 3, 5, or 7, and to deal with it, we can use quadratic interpolation to make it more smooth and good looking. Additionally, smoothing algorithm can over smooth, so cut peaks or values. To deal with it, we apply twicing. So we subtract from original our smoothing data, call it row, and apply our smoothing sequence to row and add it to our smoothing values. Here is example how it looks like. Same data, same function, but on the left we don't apply twicing, and on the right side we apply twicing once. So we can create sequence of different operations, previous operations, to create more good smoothing, and to specify them we use numbers and letters. As you can see, odd numbers is we apply median smoothing, H is for Hanning, G conditional Hanning, and Q quadratic interpolations. And down here you can see how this sequence can look like. Here is recommended one from sources. They perform well on the data. Second algorithm that we implemented is rebinding. There is 2 versions, monotonic and parabolic. So we merge bins that are most compatible until only 2 for monotonic or 3 for parabolic extremas found, then refine until statistical uncertainty is smaller than 5% in all bins. Here is example of what is extrema. So in the algorithm, left bin and right bin is always extrema. So monotonic will in result monotonic will like delete all this extrema, and parabolic keep only one between left, right, and right bins. So we implemented Twiki smoothing, rebinding smoothing, and additionally special realization function to check different algorithms on different data with different bindings to see how good algorithms perform, and we support both histogram and hist library, histogram from both histogram and hist libraries, and from root workflow, they are the most popular one to deal with histograms. Here is example of code. Here is we create some data, create histograms, and here as you can see we use one function, one universal function. Here is we specify sequence of Twiki function. User can specify their own sequence however they want, or write monotonic and or parabolic to use monotonic and parabolic smoothing. Here's for the results. For example, on the left is unsmoothed histogram, and on the right smoothed histogram. Here is example of for the root version. It's pretty much the same. We create histogram, root histogram, apply smoothing, but using root specific function. And here is results. Black one is original and red one is smooth. So to compare different algorithms and different data binding, we create grid plotting to quickly identify what best algorithm binding combinations there is. Here is function example. We specify data that we want to plot a different kind of binds and different algorithms. Here is example of different data distributions. In the legend we have different metrics to see how good this specific algorithm is for this data, and we have ratio plot underneath. So on the legend we have Kolmogorov-Smirnov test and reduced chi-square value to measure how good our smoothing apply to this data in bins variants. Here is the same but with different bins, as you can see. So there is plenty of future to work on this library. More algorithms like kernel smoothing, support for multi-dimensional histograms. Right now we support only one-dimensional histograms. Complete tests to test libraries so we don't break anything when we change things, validate our library against other libraries that already implemented, continuous integration on GitHub, and right now we docstring document every function and have examples, but we don't have complete documentation. So we can work on this too, and this is all for me. If you have any questions.
Thank you, Roman. Any questions for Roman? I don't see any questions. Thanks again, Roman. Up next is Patrikas.
Hello.
Hello.
So I'm Patrikas Styra. I was also an IRIS-HEP student during the summer, and my work was backend update of the AlCaVal framework for validation of calibration and alignment conditions. So quickly, these are contents. Academic affiliations. I have finished software engineering bachelor's, and I'm currently studying in deep tech entrepreneurship master studies. And these are my mentors, which helped me in various areas during my program. So AlCaVal background. AlCaVal is a software for testing and validating new detector conditions, which are packaged as global tags. So there are different conditions in those global tags, and those global tags have different names, even the yet unvalidated ones. So to do this, AlCaVal takes a new global tag and compares it against the reference one by calling CMS driver scripts. And this process generates plots that allows experts to validate the new conditions. And depending if they're good or not, they get updated in the database. And AlCaVal was branched from a similar tool called RelVal, or release validation, which also follows a workflow of executing CMS drivers, driver scripts, and generates outputs. So this is good to know for a little bit further in the next slides. This is basically what happened and what it is like now. And the first task was basically a monitoring and front-end task to monitor the number and duration of workflow status transitions. A background job was implemented. The job runs every 15 minutes to process the entire AlCaVal workflows table in the AlCaVal database and stores it temporarily on a file, and that file gets read by the front end, and it displays histograms, which can be filtered by date, transition duration, or batch name. So this is what it looks like in the AlCaVal application, and also I added a link to the PR on GitHub. And the second task was transition monitoring and notifying. To monitor workflows transitioning to the announced status, a polling method was chosen similarly to the previous task. And the approach will use the Request Manager 2 API. Despite some limitations like its handling of bulk requests, the API is suitable because it allows data masking to retrieve only the necessary information. So we can use that masking to quickly check whether statuses were updated for a given workflow from that API, which we can later call and store it in our own database. And the final implementation will be a job that periodically polls for workflows whose status has changed to announced, or later they also told me to check for normal archived status, since it can be quickly transitioned to it from announced. And this is also a link to the PR on GitHub. It's not merged because it wasn't checked until August 8th. And on August 8th, I'll talk about in a second. And this is what the notification in email would have looked like. You get the this ticket that was called previously RelVal. It was sort of a mix-up because the code base was basically cloned, and under it there is workflows. So there are links to each of them. And on August 8th, it was decided to discontinue the AlCaVal application, and the development shifted back to the original RelVal application. So that's why the second task's PR wasn't merged or checked. And then my task was to migrate the AlCaVal ticketing system into RelVal again. So sort of this becomes an application where you can just choose which ticket you want to create. And because they both run CMS driver scripts, they decided to abandon AlCaVal code base and put back different differences in code back in RelVal. So this work was mostly completed in this pull request, and maintainer of the RelVal project took over after my departure. So there are some additional changes, I believe, and comments by the maintainer, and there are plans, or at least there were plans, and will be, I hope, that other features from AlCaVal are also migrated back in, because there are a few nice integrations with, not sure which API, but it requests datasets, and you can put in Lumi sections by which to separate those datasets, and they get validated. So merger of AlCaVal and RelVal, this is a basic schema that what it will look like. It will be a RelVal application only, and AlCaVal will be used for the time being as a backup. And this is what the ticket form looked like and looks like now. So previously you could only create a RelVal ticket, and now you can also create what we renamed AlCaVal to ConVal for conditions validations, and yeah, you can choose between either of those forms, and they differ in fields. Like you can see, there are some global tag reference and targets, and which are compared. So that's about it.
Thank you. Any questions? Okay, no questions. Thank you.
Thank you.
Up next is Arvind.
Hi, can you guys hear me?
Yes.
All right. I'm gonna try to share my screen real quick.
Okay.
Okay, can you guys see my screen?
Yes, we can.
Awesome. Okay, hi, I'm Arvind Tawker, and my project under Professor Levage, Dr. Levage, was to develop modular ML pipeline templates for high energy physics applications. So a little bit about me. I've held previous research positions at Davis, UC Davis, where I did my undergrad as a computer vision researcher in a condensed matter lab, a data researcher at a cosmology and astrophysics lab, and more recently a machine learning researcher position under Professor Robert Bakker to do CMS collaboration. And so yeah, the project motivation was through my personal experience and from what I saw around me, HEP research relies a lot more on machine learning for tasks from classification to fast simulation. With my personal experience, I found that a lot of the code bases are quite robust and did not obey the best practices, and I personally found it quite difficult to be onboarded onto the team because of such a complex and large code base. Knowing that we have a high Lumi upgrade coming in, which is going to generate larger data sets that are more complex, we want it to be a lot easier to conduct analysis. So given that the problem statement is so vague, we wanted to sort of understand the problem landscape that researchers in HEP experience. And so we curated a survey, which is linked here. We were initially looking at maybe about 30 responses. It's not easy to get survey responses, but we went way past our goal, hitting 80 responses at the moment. And given that the survey is pretty comprehensive, we got a lot of really good data. I'm going to share a little bit of it. More of it is going to be described on a paper that we wrote, which I'm going to introduce later. So we had questions like, what your current research role is to understand target audience demographics. We got this distribution. Most of the responders were PhD students, postdocs, and faculty, which served very well for our purposes. We also had questions about frameworks, because if I'm going to make a framework, we want to make sure we're using libraries that are already popular among researchers in HEP to remove transfer overhead. And so we found that PyTorch Lightning and scikit-learn were some of the more popular ones. TensorFlow is extremely popular, but also extremely heavy and has backward and forward dependence conflicts. So we chose not to go ahead with that. There's also a study that Liv conducted. This is also outlined in the paper that we wrote, but it essentially found that about 1/3 of the papers in the HEP ML Living Review did not link their code bases. And we wanted to understand why, because this is a slight hindrance to reproducibility. And so we had that question in the survey itself. And we found that most of the people who did not upload their code or share it had their code developed quickly and was not in a clean or documented state. So that you can see that 56% of the responders selected that. And then the others were along the same lines, plan to extend or improve the library, or did not think that it was important at all. So our objective was to build a framework that makes it easy for someone to start from scratch and end up with an end-to-end ML pipeline and obeys production grade code, CI/CD, linting, etc. So we wanted two primary features. One of them was to start from scratch and end up with an end-to-end pipeline, or if you have an existing code base or an existing pipeline, you can swap out specific components of an ML pipeline just using CLI tools. The way we did this is by using a block approach, where we treated every component of an ML pipeline as a self-contained block. And normally in a pipeline, every block has dependencies that trickle down forward or backward. So if you want to change your preprocessor or if you want to change your model, you're going to have to make significant code base changes. The way we address that is by having each block completely determined by a config file that it's paired with. And so if you want to swap out a block, or if you want to swap out your model, for instance, all you really need to do is reconfigure just that part of the pipeline. So It took quite a bit of work to make sure that this worked the way we wanted it to. This is our current project structure. So the way you would use it right now is, since we haven't uploaded to PyPI, we're going to have to clone the repo to be able to use it. So we clone the repo, set up a virtual environment just to make sure we're not trickling any dependencies to global systems. And then you install the base framework. And then you can essentially use the framework and build CLI tools, which starts with MLpipe, and then you can locally install any pipeline you want, any components that you want, depending on whether you're starting off from scratch or you have an existing pipeline. And if you have a pipeline that is from our framework, then all you need to do to run it is MLpipe run. So another use case is if you have an existing pipeline, all you can do is once you clone the repo, you can install using extras just the blocks that you want, and that's going to locally install the relevant config files, the relevant Python scripts, etc. And then you can also choose the target directory where you install it. So that's going to allow you to modify your code base in a manner where you have the most control. And so, assuming that your initial pre-existing pipeline has model processing and fitting code that looks like this, most people use sklearn, so I just thought I'd use that as an example. All you need to switch now is import our block from that local location and define some basic configs, and then all you need to do is just call the fit function and then call the predict function, which is very similar to the existing code that we saw before. And this is gonna essentially use a random forest model instead of your previously existing classifiers. And if you want to swap this out again for an XGBoost model, you can do the same thing. It's the same. All I need to modify is about 2-3 lines of code, including the import. So with all of this done, the current issues that we've experienced are that the GNN pipeline does not run reliably in all environments, and I think that's just because of how the data set for the GNN pipeline works. It's also compatible with Python versions that are greater than 3.10 just because of a formatting decision that I made earlier that I'm going to have to fix later. The framework is still somewhat unstable. It doesn't work in all environments, so we're working on thorough testing. And we've written a paper on this. Sorry, this should not be under current issues. But yeah, we've written a paper on this that covers the survey analytics, the GitHub and code usage analytics from Professor Vage, and then the framework description. We've submitted that to NeurIPS under a workshop, so I'm not entirely sure if I can, talk a little too much about that because it's still anonymized. And this is the current repo link. We have a few next steps to stabilize the framework to make sure we thoroughly test it and have it work on all environments. We want to further analyze the responses from the survey. This is ongoing and will continue to be, and we want to curate or tune the branches accordingly, add some more HEP-specific support, add some more models, preprocessors, etc. And then we want to be able to get to the point where it's stable enough to publish the PyPI for global usage. That'll be all. Thank you.
Thank you, Arvind. Any questions for Arvind? Okay, no questions. Nice talk. Thanks to everybody for coming today. Thanks to all the fellows for their great talks, and thanks for the mentors for guiding them through this process. We'll have some more soon. So thanks, everybody. That's it for today. Bye.
Thank you, everyone. Bye.